Okay, it's 9:02. We can start today, Friday seminar. So it's my pleasure to introduce today's speaker, Dr. Johyun Kyoung. He is a vice president of technology and co-founder of Front Energies, the company based on Houston. He got his BS, a master and PhD degree in naval architecture and ocean engineering at the Seoul National University in South Korea. He has more than 25 years of experience working on floating platform design and many numerical analysis in academia and oil and gas industry. He has worked on floating body dynamics, hydroelastic analysis on very large floating structure, and developing in-house software for hull motion analysis and structural response. He has received many best paper awards from various conferences through the past years. Currently, he is working on developing a time domain structural analysis methodology for floating offshore wind turbine. Please welcome Dr. Kyoung today. So
Thank
whenever
you.
you're ready.
Yeah, thank you very much. Thank you. So, nice to meet you. My name is Johyun Kyoung. I'm a naval architect. I'm majoring in the numerical hydrodynamics. So major expertise that the offshore structure design and analysis, and also internal in-house program development used for the design and analysis for offshore structure. So now I'm co-founder for our company, named Front Energies in Houston. So it was a very brand new. So later slide, I will show you that some brief introduction for our company. So today, my presentation title is Multiphysics Simulation of a floating offshore wind turbine. So the renewable energy sector is growing up. So our company is doing some very traditional offshore platform analysis and design, but major focusing on the renewable sectors. So we are developing and doing some the floating offshore wind turbine design and analysis, and doing for some technical support for ongoing project. So later slide, I will make some brief introduction and what is the problem in the renewable, the offshore wind, floating wind turbine, the floating structure design. So that will be the main topic. So what I prepared is that the brief introduction to our company. So what we are doing, what we are. And the next topic is that what is the floating offshore wind turbine? And third thing is that what is the challenge in the design of the floating offshore wind turbine? So we'll pick up some the challenge things and how we are doing in the offshore industry and the renewable industries to cover this challenge. And fourth thing is that one of the dream of our naval architect is that the time domain structural analysis. So I will show you that our dreams are come true. So time domain analysis technology in the offshore, the floating wind turbine technology design analysis in terms of that some hydrodynamic part and also structure part. So, and then we'll suggest some what we are going to do to improve our this industry going forward, and also make to do some safe design and more the proper engineering. So we'll suggest some path forward things. So this slide summarizes that what we are. So who we are. So our company name is Front Energies. There are so many energies companies like Technip Energies and the other company names. So all they say the energies. So we are very thinking about what is the best word for our company. So we are Frontier. So that's why we are making Front Energy. So that's a good name. So we selected this Front Energies name. We founded 2.5 years ago, but our company is very brand new and young. but the people working for this company is not young. They are all the very large number of the years, the experience mainly from the offshore industry. So we have a core members, 7 core members. They are all coming from previously Technip. Now they are Technip Energies and Technip FMC. And also the Class Society, the American Bureau of the Shipping, and also ExxonMobil, and the SOFAC. And the CRISO is the Korean Research Institute, the only one government-funded the research institute related with offshore engineering. And the other one is the HHI, the Hyundai Heavy Industry, one of the best, the largest shipyard. And the other one is the Samsung Heavy Industry, the third largest shipyard in Korea. So these guys joined our company, and they are contribute to our company, the growing up. So as I told you, that we founded the 2021 April 15. So pandemic area. So we started at the time. And in the United States, we have the 5 employees, and Korea, we have 2 employees. So total 7 employees and the core members, and plus there's some other consultant and other people are joined. So total around 10 people. The main office is located in the Energy Corridor area in Houston. And the other office is in Korea, we have 2 offices in Gangnam, in Seoul. You know Gangnam. So, and the other one is the Ulsan area. Ulsan is the Hyundai Heavy Industry is located in the Ulsan. So we have 2 branch offices in Korea. So what we are doing is that we are providing the front-edge technologies for design and analysis of the floating offshore structures. So what is the front-edge technology? Is that we are providing the design and analysis using the CFD and also high-end the quality engineering for the naval Arctic side, the stability side, mooring engineering, and also the structure analysis also. So later slide the pick up that kind of the topic. And originally we started the conventional offshore industry project, but now we are more focusing on the renewable sectors. So one of the renewable sectors, we are focusing on the floating offshore wind turbine hull and mooring design part. And also we support the owner side engineering, and also third party the verification the work. And still we are doing the conventional offshore project like upstream brownfield project. So usually this area this time the conventional oil major company does not spend much more time or the money on the new project. They are spending or extending the life of the inbuilt structures. So that's why they are focusing more on the life extension. So we're supporting the life extension studies. And our company has two very outstanding technology. One of them is that the time domain structure analysis technologies. So this time domain structure analysis technology is very important and necessary for the floating offshore wind turbine structure, because the floating offshore wind turbine requires that the time domain structure analysis to assess the fatigue life estimation. So floating offshore wind turbine structure is governed by the fatigue. So that's why they want to make a very accurate assessment of the fatigue life. That's why they are required at the time domain structure analysis. So we developed the scalable, the time domain structural analysis tool packages named Trust. So I will show that the later slide, what is this Trust technology and how we applied this technology to the ongoing project and prosper the expected other renewable project. That's all who we are. So this slide summarizes that our capabilities. So mostly we are doing the hull and the design on the floating offshore structure, including the conventional structure and also renewable structure. Let's say that the floating offshore wind turbine. And also we provide some optimization to reduce the cost. And the most important thing in this hull optimization and design is that ILA analysis. ILA means that the integrated load analysis. So the more accurate ILA analysis is resulting in the reduce the cost of the design of the hull and also increase the safety of the hull. And wind turbine, definitely there's a blade. It's like a wing. It's a rotating wing. So we call it turbine. Turbine is controlled. So they need some controller to generate the wind energy from this wind turbine to match the maximum efficiency. That's why they have a good controller. So we provided this controller setup and the calibration technologies. And once they design the hull, and then they need to install it. So we supported the installation analysis. Installation analysis, including the towing and also mooring installation, hull installations. And third one, next one is the stability analysis. Hull should be stable. So even though there is some damages, so we call it compartment damages. There is some collision from the other supplier vessel, or inside of the hull, there is a crack that has some damages. They can be flooded. Even though flooded, they cannot capsize. They should not capsize. So that's why we check that stability analysis. So we supported that capability. And also, wind turbines operate for a long time. So it changes the environmental conditions, and also turbine itself has a lot of the maintenance issues or other things. So we supported how much the operability during the operation time, and also how much available. So we supported that capability. And the last one is that model test. So most of the offshore structures do the model test, physical model test, to confirm that this performance. And also this model test used for some reference for the numerical simulation. So numerical simulation calibrated based on this model test, because we don't have any the full scale the floaters. So before the build these full-scale floaters, we need to the model test first, simulate the scaled the structure, and then well-controlled environment is put on it, and then we get some response. And then using this response, we calibrated the numerical simulation, and using this calibrated numerical simulation, we doing the design and analysis. One of the core members has a lot of the model test experience. So we supported how we design the model test. And once the model test is done, and next step is that the correlation is very important. Correlation takes a lot of experience. So we supported that correlation. The correlation used for how much close the both result, like a model test result and simulation result, should be close together. So that has a lot of experience. We supported that capability. And next item is the time domain structural analysis. Some guys, very old professionals, he said, it's our naval architect's dream to have a time domain structural analysis. So usually the structural analysis is not doing the time domain analysis. Usually they are doing the frequency domain analysis or snapshot, very short duration of the snapshot analysis. They have not that the full time, let's say that the time step is 0.1 second, and the duration is 3 hours. They do not 3-hour time domain simulation on the structures up to now, but we developed the tool. So we can do it. We can do the time domain structural analysis more faster than the real time. Usually 3-hour simulation, the structural analysis based on our tool, it takes less than 10 minutes. So we can get a whole time domain structural response in terms of the stress, component stress. So usually the structural analysis, they are build a finite element system, and then the mapping all the external loading, inertial loading and external loading, including the transient, the wind loading or mooring loading, wave loading, drag loading, current loading, the kind of things, the mapping on the structure in the FE model, and then they get some response from the structure model. That response we can do in time domain very fast. So we'll show you later. So using this time domain analysis, we can do the strength analysis and fatigue analysis and the buckling analysis. And next item is that we support the mooring design and analysis and packages. So, and also the floating offshore structure compared to the conventional offshore structure. Conventional offshore structure main purpose is that they extract the oil and gas from the seabed, under the seabed. So they are using the riser. But the floating offshore wind turbine, they generate the electricity from the wind turbine and transferred this electricity to the on land through this power cable. So we supported how we calculate, how do the analysis on the power cable from the hull side to the on land. So power cable shape is a little bit the raised shape, as a raised curved shape. Now it's not straight line. So there's some technique to analyze this power cable. So we supported the technologies. And other than that, we also do the marine system design, the pump system, power system, the inside of the hull. There are so many the marine systems. We supported that design and also drawing. And you can see the right-hand side. So some figures show that. So as you can see, this one is the CFD analysis snapshot. So I will show you later, it's a time domain snapshot. So we supported the CFD analysis for the actual floating design. So CFD part, I prepared another slide, and then I will visit the more detailed things in this slide. This is the actual model test. So we did it in the CRISO, the Korea Research Institute. And second line is that the structural analysis. So you can see that there is some varying time of the structure response. This comes from our trust software. So, and this is a power cable analysis, the snapshot, and also boring line snapshot is provided. So we, provide, even though there are so many smaller papers are there, but we supported the kind of the capability. Even though we found it very recently, so it has only 2.5 years, but fortunately we have lots of experience on the floating offshore wind turbine project. So I'll proudly introduce how much we have experience from the project. So first, as soon as we found it, we got some project from CRISO, because that at the time, the Korea government wants to build a very large floating offshore wind turbine farm in front of the land. It's like east side of their land. We call it East Sea. Now they say Japan Sea. So, this area is close to the Hyundai Heavy Industry Yard. So this sea is the East Sea or Japan Sea. So this is the Ulsan area. So around 70 kilometers from the coastline, they want to build a very big size of the wind farm. Around 5 different wind farm sites, they are suggested. The total number of the floater is around 300 floaters, shaped like this kind of the floater. Even though there's so many the floater design suggested, anyway, that kind of floaters, 300 floaters will be installed inside in this field and generate the power, wind power. So the CRISO, so Korea government did the research institute, they want to build their own design. At that time, Korea does not have their own design for this floating wind turbine structure, even let's say the substructure, floating structure. So many other foreign companies like the Total, Technip, the kind of the companies that joined in this project, and they have their own floaters. But Korea does not have it. So they want to build this own design. That's why they contact us to design or build, design that floaters. That's why we work together with CRISO for 2 years and do some free feed and feed ready studies to generate the Korea Korea field optimized hull design. So we suggest the hull shape. It's like, we call it pentasemi. Because why it has a pentasemi? It all has a very flat surface of the hull. The shipyard in Korea shipyard, so world leading the shipyard, they prefer to using the flat panel because it is very easy to modularize and also easy to weld compared to the rounded shape. So that's some constraints. So we build that kind of the concept. So we did it. Meanwhile, there's another field, let's say the Munmubaram project. So this is a Shell-owned the field, the same field of the DCSTC. There is 5 fields: Munmubaram, other gray whale, and other things. So one of them is Munmubaram. So Shell contact us. They have another design and ask us to some mooring line design for these floaters. So we did 2 years. During the 2 years, 2022 and 23, we did the mooring line design, and also partially, we supported other technical support for the Munmubaram Shell's project. And Hyundai Heavy Industry was very interested in developing these floaters in this field. So they ask us for the technical support, the building their own their concept. Hyundai Heavy Industry also has a concept I cannot show you in this slide. So we supported the technical support to design and analysis for the hull structure, mooring, and the wind turbine, thrust, and the controllers, that kind of things. So we worked together, 2002, 22, and 23, we did it. And now, some of them knows that the Daewoo shipbuilding company merged to the Hanwha Ocean. They changed the name, the DSME, to the Hanwha Ocean. So now the Hanwha Ocean guys wants to develop their own floaters for the floating offshore structure. They contact us. We start to the free feed study this year. Maybe more exactly next year. Next Monday, we have a kickoff meeting and start to develop this hull concept, and it will last to the next year, end of next year. And this is all the renewable floaters development. And the other one is that just conventional work. We work together with Chevron. They have some brownfield work. Let's say the tieback work for their operating structure. So we support the technical issues like analysis and design. So we did it from the 2021 and up to now. And from this 4 and last to the 4 years, so we work with Anwell. So they have a spider float concept for wind turbine power generation. So we work together. So we supported the ILA analysis and model test, and also mooring line design, that kind of things. We just started this project. That's the company experience on the ongoing project. So now, as I told you, that our company major focusing on the floating offshore wind turbine. The floating offshore wind turbine has been developed very long time ago, but recently they are very focused. For example, the 2021, the Equinor presented the floating wind the FWS conference in Houston, held in the Houston. They presented the kind of things. So wind turbine industry will grown up gradually up to 2020-30, because that the Korea government did the wind turbine project is the world first wind turbine project, floating wind turbine project, ongoing project. They are expected to start this project 2025 and complete the 2027. And also the United States, they also started this floating offshore wind turbine, and they are targeted 2030, 15 gigawatt, the production from the floating wind turbine. And also in Europe, they're also doing 2025 to the 2027. They want to build and install all the floating structures, several offshore floating structures. That's why Equinor said up to 2030, there's gradually increase. And then after that, the field is already built and operate. They got the experience, and also supply chain issues there. Supply chain issues will be solved within that period. So they expect that after 2030, we will be exploded. So everybody do this floating offshore wind turbine. That will be market will be exploded. They expect it. So currently, the key geometrical graphics, the focusing on this offshore wind turbine, definitely the EU, the UK or France has very eagerly investigated and invested, and also United States. They are targeted to 2030 for 15 gigawatt in the West Coast and East Coast, and even Gulf of Mexico. They already announced that lease, right? Is the Louisiana field and the very near shore field, they already announced that the lease. So some companies already, taken action. Definitely, Korea is the first one to build some floating offshore wind turbine, the large farm, and Japan, Brazil, and India, the Vietnam is they are all the focusing on it. So that's a status, and also for the floating offshore wind turbine. Why floating offshore wind turbine? So most of the offshore wind turbine is installed in the near shore. The water depth is less than 30 meters. Yeah. So they have put some single pile on the seabed, and the other tower, and the turbine is installed on top of that this pile. But as you know that wind energies grown up as far from the coastline. The problem is that they cannot install the single pile on the seabed because the water depth is more than 60 meters. The pile system cannot support this tower. The mechanical issue and the foundation issue, and also the vibration, natural period resonance, that kind of things. That's why they think about the floating offshore wind turbine. So more than 100 water depths, definitely should be floating offshore wind turbine system. So up to now, the offshore industry, we can say that around four characteristic floaters are available. One is the definitive ship shape. Other three is that semi-submersible, as we can see, semi-submersible shape. And second one is the spar shape. Spar is just a single pipe, very long single pipe. And the other one is the tension leg platform, TLP. So three different kind of the floaters design concept can be applicable to the floating offshore wind turbine. Compared to the conventional offshore structure like topside supported all the processing unit for oil and gas. But a floating wind turbine, so compared to the conventional topside, it's very light. It's less than 2,000 tons, include the tower and the blade, the rotor and nacelle. All these things around the 2,000 tons up to now. So biggest of the turbine cases. But problem is that it's too tall. The tower height is 150 meter. Blade, one single blade is 120 meter. Diameter is 240 meter. It's too huge. So quite large moment is affecting on the floating structure. That's the one thing. Second thing is that it's a rotate. Keep rotate to generate the power. Rotating structure generates some vibration. This vibration produces that fatigue. So that's why substructure and this floating offshore wind turbine structure suffering fatigue issue. It's a major concerning. So that characteristics, we need to consider that. And also three different kind of the floaters like semi, spar, and tension leg platform. They have a different characteristics. So according to the exciting or vibration, some floaters has a resonance, some floaters has a too big, some floaters are too lengthy. The kind of the characteristics. So investor or the farm builders or engineering company is juggling these three different concepts to optimize that some application for the field. So mostly in Korean field, they are prepared to use a semi-submersible concept because this semi-submersible concept can be applied to the quayside integration. Quayside integration means that they can build all the structure in the quayside. Quayside means the shipyard, and then bring this hull to the operating in place, and then just do the operation. Very easy. Spar is very lengthy, so it cannot build in the shipyard. So they bring the spar hull to the very deep water depth position, and then they are appending. Let's make a straight appending, and then install the top side and the turbine. So that's offshore operation is additional operation is necessary. Tension leg platform, they need some tendons connecting to the floaters and the seabed. It's very tight tendon is necessary. So tendon this tension platform has some very higher frequency resonance because of the tandem. Sometimes this resonance coincidence with the tower, the resonance. So that's a fatigue issue. So even though they have some solution to replace the tandem material to the other material, or they change the whole concept, but anyway, the kind of the things. So anyway, these three different kind concepts worldwide, they are suggested. So when he researched, when he started this design, when he researched that how many concepts are available in the website or worldwide, we found that around 1,000 concepts is suggested. But nowadays, very expert people, let's say that principal power, they are firstly they installed the floating offshore wind turbine structure in Europe. One of the guys that maybe later, maybe 3 or 4 concepts will be survived from this 1,000 concept they expected. That's a floating offshore wind turbine, the market. And I would like to say that, so what is the challenge in the floating offshore wind turbine? So you can see this is the Okaplex model, the scaled model. So recently, the investor or the operators, they are thinking about the 15 megawatt wind turbine for the floating wind turbine, the operation. The 15 megawatt wind turbine has a diameter is 240 meter, and rotor center means that this hub center from the beam water level is a 150 meter location. So when I Googling, so I found that how much bigger. So you can see the Boeing 747, you can overlap the 3 Boeing 747 in the one single rotor diameter. That's the kind of the size, very big size. And also the Frankfurt, the Trade Center Tower, the height is 256 meters from the ground to the top. The wind turbine from mean water level to the top of the rotor tip, the blade tip, is 236. It's close. That kind of the size, very huge. But weight is not so much. Usually conventional, the offshore, the processing unit topside is at least the 10,000 ton, metric ton, but it has only the 2,000 ton. So weight is very small, but very tall and very big size of diameter. And also it produced that thrust, a lot of thrust. And that makes also the rotation vibration. That makes the fatigue issues. So that's the one thing. The physically is very huge size. The other thing is that it has a multiphysics system. So multiphysics system is that it including the aerodynamics, because the blade generate the power. So it based on the lifting force. And also it involves some control system. So servodyne is involved. And also it floated. So hydrodyne issue. So wave energy is we need to consider that. And the last thing is that all these things is elastic body, not rigid body. The blade is very thin and length. So it has a flexible, very flexible. Even tower has a flexible. So all these things is elastic body information. So we need to solve this problem, aerodynamic side, servodynamic side, and also hydrodynamic and elastic behavior also. So that's why the Rural Society and other this turbine related society, they are suggest how to solve this problem. They suggest the time domain. All the things are time domain analysis. The motion analysis is okay. We can do the time domain analysis, but they require that the structural analysis also in time domain. So at the time, so when he started this study, there is a very few the commercial software doing the time domain analysis. They can do the time domain analysis in the structural analysis, but was not practical. How much the impractical is that just a simple the semi-submersible structure. We want to solve that the 1 hour simulation time step is at 0.1 second. That commercial tool takes a day or week to solve this problem. It's impractical because we need to do this time domain analysis for 2,000 cases, 4,000 cases. So one single run takes a one day or 1 week. It's impractical to do some engineering analysis. So another technical tool is that safety analysis. So we developed these safety tools from the maybe 10 years, the developing period. So we have some brand name is FOWT. It's a safety-based numerical wave basin. We can do it the floating offshore wind turbine in the safety domain. So using these safety tools, so we generated the waves, irregular wave, C-state wave, and also floating body analysis. And also there's some mooring line risers attached together, and there's a wind turbine is attached. We can do it. So the safety analysis, what is the important thing is that usually when we design these floaters, we do the physical model test. Physical model test, we need to occupy or make a slot for the physical model basin. It takes 6 months. And also they need to prepare the model and prepare all the setting. It takes 3 months. So after model test, we need to get some result, and it takes 2 months. But CFD, when you generated this model, it takes 1 day. And CFD analysis, it takes 1 day. And then we can get a result only 2 days. That's why we're focusing on the CFD analysis. Even 3 hour simulation, it takes 1 day. So we have some tech knowledge. So this safety technology is very important on the floating offshore wind turbine design analysis, because there's so many uncertainties without model test. Even model test, there's so many limitations, because that currently model basin cannot exactly replicate this turbine modeling, because that it has a different similarity rules, and also they have some difficulties to simulate some flexibility and also corresponding the control system. That's why they made some approximately the wind turbine in the model basin, physical model basin, but safely we can model as it is. So that will have more the benefits for the simulation. So we used these simulation techniques for the ongoing project. So Graywell, GW3, the FEED study, Hyundai Heavy Industry, using the CFD technology to capture the damping plate optimization. And also Chris also using these technologies for the pentasemi development. The next thing is that time domain structure analysis. So we developed this tool. So using the finite element system and the ILA result, we can get a time series of the structural response as it is from the structural model. That's our tools. So the main object of this developing the time domain structure analysis tool is that we don't want to missing any missed load cases, because that okay, conventional the time domain tools, it takes a long time, so that's why they pick up that the very small duration of the simulation to pick up this time domain analysis. But we don't want it, so we solve the whole time series of the structure response. So through these tools, you can get a time series of the stress component for the whole duration of the simulation, like a 1 hour simulation, 3 hour simulation, you can get it like this. This is the animation of the time domain analysis. That's a valuable tools. That's why the shipyard in Korea, they start to using it. So Hyundai Heavy Industry, their Gray Whale project, CIP project, using these tools, they are validated all the structure response. And also KR, Korean Registers Class Society in Korea, they using these tools, they build guidelines. And Hanwha Ocean, now they are start to using for their FLIPID study. So based on our capability and also analysis, the capability, we don't want to keep these techniques inside of our company. We would like to share that. Yeah. We'd like to share the other company, our industry. That's why we are thinking about some JIP. So we call it the floating offshore wind turbine, the FOWT, the CFD JIP. Through this JIP, we shared these tools like a CFD technology for the wind turbine project and also time domain structure analysis for the wind turbine project. And we want to build some the user groups and provide some training for how to use it. And then eventually would like to build some sample the analysis toolkit. So that's why people using this sample, they can apply their own structure to apply these tools, like CFD tools and structure tools. They just change the geometry and the properties, directly use it. So would like to share these tools through this JIP. That's our, the passport idea. Yeah, that's what I have today. So thank you very much for the attention. And in the audience, is there any
question? Any question to, yeah.
Oh, yeah. Yeah, that's usually this multiple floater types. They have their own characteristics. Like some product is very easy to build. Some floaters has very good motion responses, and some product has a cheaper the cost, that kind of things. But even though, for example, the good motion product you selected, but it takes additional operation cost. So they are juggling. Which one is better for us? And that's one thing. Second thing is that most of this wind turbine project is localized. Korea, they want to build a Korea shipyard. EU, they want to build their EU shipyard. There are different capability for the fabrication. For example, Korean shipyard, they can handle the very big size of the chunk of the module, but EU, the shipyards, they can handle the very small members. So they are thinking about, oh, which one is better? Yeah, so that's why. Depending on this one, they selected these floaters.
So any other question?
I'm wondering if these offshore structures are feasible in the Gulf of Mexico, given the extreme hurricanes that occur pretty frequently here.
Yeah, right. So one of the load cases, design load case, they consider that kind of wind, the environment. That wind environment condition, like hurricane condition, they cannot produce that power. Let's say we call it parking condition. They change the pitch angle to the weather vane feathering state and does not provide any rotate, does not rotate. So fix it. Just endure that this environment. We consider that.
Yeah, I'm wonder. So how do you transfer the energy generated by the wind turbine to land side?
Yeah, wind turbine has a connected power cable. This power cable connected to the substation. Substation grabbing all the powers produced by individual floaters, and then grabbing, and then they send this power to the on land. There's some power station. Yeah.
Okay. So no more question in chat. I think no more questions. So we can close this seminar. Thank you very much, Dr. Gi. Chat, no question. Oh yeah. Oh, sorry. So one question. For mooring analysis on slide 9, there are branched mooring, one motor that you use to motor two branches. Spring motor or constraint?
The mooring model is our patented mooring model. As we say that Y-shaped mooring line. So yeah, constraint is that the close to the hull, there is a short line, is a chain or wire, and the rest of the line is definitely chain. Yeah, and then it looks like floating, but no, it's a seabed. It's not floating. It's a viewpoint makes it a kind of the illusion. Yeah. So end of the chain is there's the anchor. Yeah, anchor, we can use the pile anchor or drag anchor. Yeah, there's so many types of anchor. So currently we are using the drag anchor.
Okay, any other question in chat? Could you add more branches to mooring?
Mooring, number of mooring are very expensive. So would like to reduce the number of mooring. That's the main purpose. So that's why we have that kind of Y shape. Otherwise, yeah, definitely, yeah, right. We can put some additional mooring line. It's a very conventional mooring line. Each column has a 2 mooring line. So that's why total 6 mooring line, we can configure that.
Okay, reserve it. Is there any other question? Okay, we can close this seminar series. Thank you.
Thank you very much. Thank you.